Okay, let's have a look at the third graph now. You'll notice the other two graphs have been erased. That's just because when I start a new video, I have to start with the PDF file from scratch again, so don't be confused by that. But let's have a look at the third example. Okay, so your third graph, we can see from the equation, has roots at 2 and -4. And using the exponents in the equation, we can see that 2 is a single root because the exponent on that factor is just 1. And -4 is a triple root because the exponent on that factor is 3. Okay, so we have a function here that has a degree of 4. So this is a quartic function. And this time the leading coefficient is -1. Okay, and since the leading coefficient is negative, we'll say this is a quartic negative function, which tells us that the end behavior for the function will be from quadrant 3 to quadrant 4. Okay, so we'll mark off our roots at 2 and -4. And we'll also find the y-intercept by replacing x in the equation with 0. And then we can see that our y-intercept is at 128. Now, for the purposes of our sketch, I'm just going to choose a random point on the y-axis and label it as 128. You can do that when you're just sketching the graph, okay? We don't have to worry about what exactly the scale would be there. So we won't mark off the other tick marks on the axis. We'll just mark off where our intercepts are and where the y-intercept is, okay? And that's often what we do. Now, our end behavior is Q3 to Q4, which tells me my function is going to be sort of originating in quadrant 3, traveling through to quadrant 4. Also, the behavior of the function at -4 is going to be like the graph of a cubic function because this is our triple root. So it's going to travel through the root like that, and I knew it was in that direction because of my end behavior here starting in quadrant 3. And the other root is a single root. So on this side, my graph is just going to go straight through the root. Now again, since my y-axis is closer to the intercept at 2, I know that 128 is not going to be a maximum point. Okay, the maximum point would be a little to the left of that. So we'll show that by having our graph kind of go up past it, sort of like that. Okay. Now in the next example, we're sort of doing the opposite. We have the graph and we're asked to come up with the equation. So in this first one, I'm going to use the intercepts to begin with. So I've got intercepts at -3, +1, and +2, and they all appear to be single roots. So I know my equation is going to be y equals a times x plus 3 times x minus 1 times x minus 2. Now, the a value here is sort of our unknown at this point, so we don't really know what that value is, but we could find it using the y-intercept. So we're going to let x equal 0 and y equal 3 in the equation. So now we have 3 times -1 times -2. So we'll have 3 equals, on the right hand side we've got 6a, so divide both sides by 6. And we can see that a equals 1/2. So therefore our equation is y equals 1/2 times x plus 3 times x minus 1 times x minus 2. Okay, we'll go through those steps again for this next one. So on this graph I can see my x-intercepts are at -3 and 3. This one, the negative 3, appears to be a triple root. This one appears to be a double root. So in factored form, I'm going to start with my equation as y equals a times x plus 3 cubed, corresponding to my triple root, times x minus 3 squared, corresponding with the double root. And then once again, we'll use the y-intercept. So we'll let x equal 0 and y equal 30 in our equation to find the a value. So 30 equals a times 0 plus 3 cubed, 0 minus 3 squared. So this would be 27 times 9. So 30 is equal to 243a divided by 243. And we can also reduce this fraction on the left. Dividing by 3 reduces that fraction down to 10 over 81. So our equation here is going to be y equals 10 over 81, 10 over 81, x plus 3 cubed, x minus 3 squared. Okay, and the last thing we're going to talk about in this rather long lesson is the concept of odd and even functions. So an even function satisfies the property that f evaluated at negative x is the same as f evaluated at x. I'm going to show you what that means algebraically in a moment, but for now what that means graphically is that your equation is symmetric about the y-axis. So the y-axis acts like a line of symmetry here. So on one side of the y-axis, your graph sort of can behave like this. This is just an example. Okay, and looking on the other side of the y-axis, your graph is symmetrical to that. So basically you could fold your graph along the y-axis and it would match up. Okay, so graphically that's what an even function would look like. Now an odd function satisfies the property that f at negative x is equal to negative f of x for all values in the domain. Again, we'll look at this algebraically in a moment, but graphically what that means is that there is a point of symmetry at the origin. Now that is something that's new to you. You know about lines of symmetry. A point of symmetry means if I have a point of symmetry at the origin, you can see that this graph is the same to the left, the shape is the same to the left, we should say, as it is to the right. So if I were to rotate this graph sort of about the origin, that graph would line up on top of itself. So that's a point of symmetry. Okay, so odd functions are point symmetric about the origin. Now something that's important to note here as well is that it says not all even functions, not all even degree functions are even functions, which seems a bit strange. So an even function and an even degree function are not exactly the same thing. Now in order for a function to be even, it does have to have even degree. Okay, but it is possible for an even degree function to not be symmetric about the y-axis. We've seen some of those already. Similarly, not all odd degree functions are odd functions. Okay, but only odd degree functions can be odd functions. So now we're going to look at how you show algebraically whether a function is odd, even, or neither. So in this first one, we first look at the degree of the function, okay? So this function has a degree of 4. So that might be an even function. Okay, so we're going to test to see if this is an even function. You will never have to test odd and even. Let me fix this so it's actually legible. You'll never have to test for odd and even, because as soon as you see that a degree is even, you know it might be an even function, but it's definitely not an odd function. Okay? So first we're going to evaluate f at negative x. So you have your equation for f of x, and you're going to replace all of the x's with negative x. And then you're going to simplify. So negative x in brackets to the exponent 4 is just x to the exponent 4. Negative x in brackets squared is just x squared. So it'll be minus x squared plus 2. Notice that's exactly the same thing we had to begin with. So since f at negative x is equal to f at x, we can say that f of x is an even function. Okay, with this next one, the degree is 3. So this one might be an odd function. It has odd degree, so it might be an odd function. To determine whether it is, we have to evaluate f at negative x. So replace all your x's with negative x's. And simplify. So that will be negative x cubed minus 3x. And we must also evaluate negative f of x, which we do by making the whole function negative. Okay, so what that's going to do is basically change the signs on each term. Now notice these two things are the same. So we say f at negative x is equal to negative f of x. Therefore, f of x is an odd function. Okay, and one more example. Again, our degree here is 3. So this is an odd degree function. It might be an odd function. So we're going to evaluate f at negative x by replacing the x's with negative x's. We're going to simplify. So we'll have negative x cubed plus 2x squared minus 3. And we're also going to evaluate negative f of x by making our whole function negative. And we do that by changing all the signs on the terms. Now notice f at negative x does not equal negative f of x. These are not the same thing. So therefore, your function f of x is neither odd nor even. Okay, in this case it's neither. And finally, that concludes this lesson.